Okay, here we go with the next section, 3.3. I'm going to reiterate some of the stuff I gave you in the review of rational functions, and we're going to take it a little bit further, okay? We're looking at a little more detail. So first of all, still we're looking at a rational function being defined as a polynomial over a polynomial, okay? G of x and h of x, or whatever you want to call them. Your numerator and your denominator are individual polynomial functions, and one of the biggest keys here is that your denominator cannot be zero, right? And that denominator of zero, or whatever makes your denominator zero, is what we call a restriction. And that gives rise to these things called asymptotes, okay? A vertical or a horizontal line that the graph approaches but never touches. The vertical asymptotes are significantly easier to find. They involve simply the restriction. So whatever your x cannot be, that is a vertical asymptote, all right? So if I had a function that looked like this, 2 over x minus 1, or x minus 2, sorry, you'd see that x can't be 2. So your vertical asymptote is at x equals 2. And that is just a vertical line at x equals 2 that your graph approaches but never touches. Okay, we'll look at graphing them again in more detail very, very shortly. We're just going to look at a bunch of terminology and a few techniques to help us figure out some points and a better idea of what these graphs look like. Horizontal asymptotes are the next ones, and we can find them in two separate ways, okay? The first way is what I showed you in the review. You simply pick a large number and find out where your graph is going. So for this one, for example, if I just chose if x was equal to 1,000, I'd have 2 over 998, which is pretty much, I don't know what it is exactly, but it's almost 0. So you know that your horizontal asymptote would be at 0. Okay, that is one way to find your horizontal asymptotes. Okay, the next way involves a few different steps here. Okay, so if the degree of the denominator is larger than that of the numerator, your horizontal asymptote is y. What the hell does that mean? Okay, well that means that if your function looked like this, 2x over x squared plus 1. Okay, if you tried a really big number here, you'd end up with, say, if x was equal to 100, you'd have 200. Now 100 squared would be 10,000 plus 1, so 10,001. Now this is getting smaller, maybe smaller, slower, but it's still getting smaller and smaller and approaching 0, right? So if the degree on the bottom is bigger than the degree on the top, you're pretty much guaranteed that your horizontal asymptote will be 0, okay? Now there's another section. If the degree on the top and the degree on the bottom are the same, well, let's have a look at that. So if I said 2x squared over 2x squared minus 6x plus 2, in this case, your your degrees are the same on the top and the bottom. Then what they're saying is that the leading coefficient, let's make this a 3 here. What they're saying is that the horizontal asymptote is going to be this 2/3 here. Now, plugging large numbers in here would be a pain in the ass to do. You wouldn't be able to necessarily find 2/3 very well. So there is a process by which we can solve these. And that is dividing the top and the bottom, every term, by the highest degree in the denominator. What that means in this case, you divide by x squared. Every term, so 2x squared over x squared, and then the bottom would be 3x squared over x squared minus 6x over x squared plus 2 over x squared. Okay, so this is, down here, we divide by highest degree in denominator. This will be the most effective way and most accurate way, and probably the quickest way to find that horizontal asymptote, okay? And the idea here is this, okay? Because if you cancel this out, boom, that goes away, that goes away. So what you end up having is 2 over 3 minus, and here you have 6 over x squared, or sorry, just x, and then you have 2 over x squared here. Now, the reason these goes away, because what happens is this: if you have 1 over x, okay? And you're looking at your horizontal asymptote. So what's happening way over there or way over there? What you're looking for is this thing called the limit. What happens as x approaches infinity here, right? Because if your graph's going way over here, your x is approaching infinity. And as x approaches infinity here, you can see that this value is equal to 0. This is one of those crucial things to grasp. Now, what we can write down here too is that maybe put that up here. 1 over infinity is equal to 0, right? Maybe you can write this down as well because that explains what's happening as x approaches infinity, or even if it goes the other way, negative infinity, okay? It's always going to be 0. And the idea is that when you divide by that degree, everything cancels out, and you're left with that 2/3. We'll look at that again very shortly. And the other thing, the last thing that you want to look at, these are kind of tricks to help you figure out if there even is a horizontal asymptote. If the degree on top is larger than the one on the bottom, then there is no horizontal asymptote, but we can have what we call a point discontinuity. Okay, so what we should probably look at, we'll look at a few examples, but right now I'm just going to explain quickly again what a discontinuity is, okay? And what you can think about a discontinuity is that they are kind of where the graphs are broken, okay? Either as an asymptote or there could just be a point that can exist, okay? So we call that a point discontinuity. First of all, they can be asymptotes, vertical or horizontal, or they could be holes, these things called point discontinuities, okay? These are a break in the graph, and they occur when simplifying rational equations, so you can cancel something out. And if you cancel something out, then that is actually a point discontinuity, all right? Now, they're also called removable discontinuities because we can actually take them out. They are being canceled out, and if you remove the discontinuity, the graph kind of stays the same, okay? What I showed you in the last chapter, and I'll show you again in the last video, and I'll show you again really soon, is that you can have a line that just has a dot in it, right? You can have a line that's your function, boom, but it just can't exist here. So we put an open circle. Okay, so you can even have an open circle, which is a whole point discontinuity. Notice that it goes right through. And the other thing is an asymptote, right? The other thing is an asymptote that your graph gets close to, but never actually touches, okay? They're a little bit different. So you can have a point discontinuity, or you can have an asymptote. So let's look at a couple here. Find the asymptotes in the holes. Okay, so first of all, if you look at this thing, you can see that it's x minus 3. If you factor the bottom, it's x minus 3 over x plus 2. Well, you can see, first of all, that my vertical asymptote, right, is x equals 3 and negative 2. So if you were going to graph it, you're going to have two vertical asymptotes at 3 and negative 2. Or actually, you're going to have two possible things. Okay, hold on, that's wrong, actually. Because what you're going to do is you're going to cancel these out. You're going to end up with 1 over x plus 2. So you have two things, right? You have two possible discontinuities, 3 and negative 2. Since you canceled out x minus 3, it means that x equals 3 is a point, or a hole. Let's call it a hole discontinuity. And because the x plus 2 remains the same, it means that x equals negative 2 is your vertical asymptote. Okay, so it just gives you an idea of which is which, because with the asymptotes, what we do is we kind of curve it smoothly to that asymptote, right? But with the points, it goes right through. So it's good to know which is which. Now, let's have a look at another one here. X squared plus 2x minus 8 over x plus 4. Did we find a horizontal asymptote here? We didn't actually find a horizontal asymptote here, but let's look at our statement here. If the degree of the denominator is larger than that of the numerator, the horizontal asymptote is y equals 0. So what we had here, let's finish this off. Vertical asymptote at x equals negative 2. We have a hole at x equals 3. You have a horizontal asymptote. Let's just try a big number. If you put 1,000 in here, 1,000 over 2, and 2, 1 over 1,002, so your horizontal asymptote is at 0 there. Okay, so first of all here, you can identify your vertical asymptote right away, right? But let's simplify this if we can. X plus 4, x minus 2, all over x plus you can see that that's going to cancel out. You're going to be left with x minus 2. Well, in this final version, you'll notice that you have no denominator. So it's going to look simply like a line, right? It's going to simply look like a line that goes down to, and you go like this. There's your graph. However, you did have a canceled out version. So this x equals negative 4 is what we call a hole. So at negative 4, 1, 2, 3, 4, boom, right down here, wherever it is, okay, you're just going to put a circle, erase the line in the middle, put a circle, and that's your point discontinuity. So at negative 4, you have a hole. There is no horizontal asymptote, and there is no vertical asymptote. Does that line up with what we're saying here? Check it out. If the degree on top is larger than the degree on the bottom, which is a situation here, degree on top larger than the degree on the bottom, there is no horizontal asymptote. You will have a point discontinuity, like we just talked about. Now, if I'm going too fast, guys, just slow the video down. Maybe I should talk slower. No, I'm not going to do that. Let's see if we can simplify this one here. So x plus 2 on the top, x minus 2 on the bottom, and we can break down the bottom by taking out an x, and you have x squared minus 4, so it's still going to be x plus 2, x minus 2, you're going to have an x, and you're going to have an x plus 2, and an x minus 2. So this whole thing cancels out, bang, bang, into 1 over x. Now hopefully you remember what that 1 over x looks like, right? 1, 1, negative 1, negative 1, and you've got this graph that looks something like this. Okay, but don't forget that you have, so first of all, your vertical asymptote at x equals 0, your horizontal asymptote, since the bottom is bigger than the bottom is a larger degree than the top, it means that I have a horizontal asymptote at y equals 0 as well. Now the point discontinuity, where are your holes? They are the things that you canceled out. So you'll have it at x equals positive 2 and negative 2. So at 2 you want to put a hole. At negative 2 you want to put another hole in your graph. Okay? So holes and asymptotes. Lots of stuff to think about here, ladies and gentlemen. And I think I might leave it there. Okay, we'll look at graphing these in the next section. Keep plugging away at this, folks. You'll get it.